Control. I did a podcast with him, actually, one of my early guests. He's a very interesting, smart guy. He's going to talk about enabling useful quantum computing for enterprises with quantum infrastructure software. Please join me in welcoming Michael.
Great. Thanks, everybody. It's wonderful to be here. I want to tell you a story in the next 20 minutes or so, and I want to frame it around where we are and where we're trying to be in terms of making quantum technology, quantum computing in particular today, useful as a computational tool, making it something that enterprises want to buy and want to use. And I want to achieve three things in this talk. First, I want to tell you what those real barriers to adoption are today and how we're trying to overcome them. I want to share with you insights into how Q-Control is focused on solving some of the biggest problems. And I want you at the end of this talk to understand what this weird-looking thing is in the background of this presentation. So you're going to learn all those things as we go through this talk. Now, as a company, we're focused on two distinct verticals in quantum technology, that is quantum computing and quantum sensing. We've heard a lot about both of these in the last day and a half. We have a huge focus on how quantum sensors can be used for inertial navigation, can be used for gravimetry, can be used for defense and intelligence purposes. I'm not going to talk about any of that today, so please do ask me if you'd like to hear more. I'm instead going to talk about the products that we build with a focus on making quantum computing useful, focused on infrastructure software. If you're not familiar with Q-Control, I want to just give a quick snapshot. I founded the company in November 2017. We have since grown to almost 120 staff members in the United States, Australia, Germany, and the UK. We were very proud, although this is a vanity metric, we raised the world's largest Series B for any quantum software company. But much more importantly is who we are helping. We serve, actually now, I think today, over 16,000 individual users of our various software products. We've connected our technology to almost 24 hardware partners, and we work all around the world with major enterprises, government research laboratories, and academics trying to help solve the biggest problems in the field. Now, all of us are here broadly because there is a recognition that quantum technology has an enormous potential for impact. And I think most of us in our daily lives, especially those of us who are founders, will quote Jean-François and his team at BCG, who indicated that quantum computing has the potential to deliver $850 billion worth of enterprise value by 2040. And that's because it touches so many distinct areas. We've heard a huge amount about machine learning, also pharmaceutical drug discovery, optimization, material science, pharmaceuticals, new forms of quantum-enabled finance. Quantum goes to so many different places, and that's why the potential impact is so large. Now, in this field, looking to make this real, we build AI-powered infrastructure software. Infrastructure software that connects the actual physical devices, the low-level things like chips and control electronics, to the high-level abstractions, the things that people build as programming frameworks and developer tools, words that you'll hear like Qiskit and Cirq, these high-level abstractions. We build the glue between them. And when I say AI-powered, I do not mean ChatGPT wrappers. I mean that for the last 6 years, we've been building our own machine learning agents that help us interact with the hardware to solve some of the really, really hard problems. The vision that we have, and the story I'm going to be sharing with you for the rest of this talk, is the idea that we want quantum computing to be a useful tool. We want it to be integrated into the way we process information today, and that ultimately means that we're trying to achieve some kind of hybrid integration, that we combine the best of classical and quantum technologies. I think this should not be contentious. The key question is, how do you do it? Now, our focus is on enabling that with the glue. quantum infrastructure software. And for those of you who are familiar with enterprise software, the analogy that we sometimes use is that we're like VMware. We virtualize the underlying hardware to make this possible. So you can run any application on any quantum processor, any CPU, and any GPU. The challenge is that there is an enormous impediment standing between us and that high-level vision. And that is the actual user experience that anybody has when they go and they run something on a quantum computer. If you run something, if you execute a program on hardware, which is the only way that we should be doing anything, frankly, you may hope to get a particular answer. This is a Grover search algorithm for those who are in the know. We're trying to identify a missing needle in a haystack location. That's the big peak on the top. But when you run it, what you get is the bottom. And the important message is that they don't look anything alike. You don't get the right answer. The hardware failures mask the insights that people are trying to get from execution of these algorithms. Errors are the Achilles heel of this technology. Now, if you are an expert, you will go through a process by which you string together a whole slew of things. For those of you in the audience who are looking at this with eyes wide open and horrified, that's the point. Because most people have no ability to go through the process of orchestrating all of the specialist techniques at the hardware level that are required in order to reduce errors and get useful outcomes. It's extremely hard. So by analogy, we see that there is this tremendous gap between the skills that exist in enterprise and government of how we run classical information systems, and then the strategic advantages that we're all trying to get. It's so hard to actually get useful performance out of these machines. Now, of course, expert teams like ours specialize in this, and many of my colleagues here, but that is such an extraordinarily small slice of the global user base. This is the challenge. But it does not need to be this way. We build performance management infrastructure software, and we're very proud that in December of last year, we natively integrated this performance management infrastructure software into IBM Quantum. So one of the very large providers of quantum computing access. You can go to IBM Quantum right now, and there is an option for Q-Control performance management, or you can access this via our cloud service called FireOpal. All of that horror that I showed you on this previous slide with the black and red annotation, all the expert level configuration, is now turned into one command. And that one command is to set the channel strategy in Qiskit to Q-Control. That's it. A developer who has classical IT skills is more than capable of doing that. There is nothing quantum that has to be done in order to get extraordinary performance benefits. Now, I made sure I included something for the experts in the room who wanted a little bit more meat. What's happening in the background is that we have built a complete orchestrated workflow where we combat error everywhere that it occurs in the hardware. This is something called error suppression for the experts. We have a compiler, we have AI agents that figure out the best layout to map your circuit to hardware. We have AI agents that redefine the machine language for the entire process. We have AI agents that help combat errors in readout. All of these things are strung together and orchestrated invisibly in that one command. Set channel strategy equals Q-Control. You don't have to worry about it. And it delivers actually ridiculous numbers. Numbers that I am often afraid to cite the actual numbers because they stop being believable. More than 1,000x performance enhancement on test algorithms that are widely run in the ecosystem called Bernstein-Vazirani for the experts. You can achieve on large processes more than 99.9% confidence that you've actually gotten the right answer. If you run a certain kind of algorithm relevant to optimization that I'll show you in just a minute, more than 100,000 times performance enhancement over the bare metal approach, and you can run at full processor scale. Not tiny little test algorithms, you can run things on the full devices that are offered by IBM, over 100 qubits. This performance is achievable with any application. We were very proud, therefore, that when we announced this with IBM in December, we actually had a billboard and a congratulatory message in Times Square from NASDAQ. The one application that we've thought quite a lot about is optimization. And I want to impress upon you that this is something worth paying a lot of attention to now. You've heard about it, but I want to tell you a little bit about why this is exciting. Now, we work directly with a variety of organizations, in particular the Australian Army, Transport for New South Wales, and Network Rail in the UK. And the focus has been on how near-term quantum computers can solve the very hard problems that they have. And I want to emphasize something important here. These are not necessarily problems where you can prove with pen and paper that you can get huge performance advantages. But it doesn't matter, because the classical solutions are not delivering for these end users. All they want is something that works. This is why we see near-term opportunity. So one class of problem that many of you have probably heard about is called max cut. This is a machine learning problem. Many, many problems can be distilled into this mathematical problem, which says pretty simply, if you have a bunch of things that are connected together in this object called a graph, you want to figure out the right way to cut it in half into two pieces where you maximize the number of cuts you make. That's the max cut problem. Now, it's pretty easy intuitively when the graph is small, but as the graph gets big, it actually gets very difficult. It's extremely hard to understand what the right set of cuts is. This is a problem known to be amenable to solutions from quantum computing. And one of the algorithms that is widely employed in this is called QAOA, Quantum Approximate Optimization Algorithm. It's a hybrid algorithm. It uses a little bit of quantum inside a bigger classical process in order to try and solve these problems. Now, it's great because it runs on today's machines. You can run it on small processors, but you can't really prove with pen and paper that it's going to give you some huge boosts. And more importantly, it's actually pretty hard to run and get useful results out of. So the first thing I wanted to show was that you can actually start to solve problems better than you've ever been able to before with Q-Control software on our partner IBM's hardware. This is a set of data that were published originally by JP Morgan on an alternate hardware backend, and they show that as the problem gets bigger and bigger, they struggle to actually solve the problem correctly, to find the maximum cut. But in this case where we're running Q-Control software on IBM, we find the problem solution, the max cut, in all of these instances. And I want to emphasize for the experts in the room, this is 100% executed on hardware. There is no classical cheating, there is no simulated first and check. The whole thing is run on hardware, the entire hybrid algorithm, and it's 30% faster than running just the one instance on the bottom. More importantly, you get the right answer. Now, we were really excited that in December we were able to show you could go beyond that, those problems with 30 qubits or 32 qubits, and run algorithms with 50 qubits. Now, the signature that QAOA is working in this particular graph is that the purple histogram, the distribution, shifts to the left. What that's saying is that when comparing against a random search, like brute force selection, running the QAOA algorithm pushes you towards larger cuts, toward answers that are more valuable. Now, we were quite excited because we find the maximum cut in this problem, which, again, giving something to the experts, it's a 3 regular graph, it's a classically hard problem, it's not the device topology, it's actually a hard problem. So we were excited that we get this shift with 50 qubits. That was in December, and because we don't rest on our laurels, here's where we are today with 100 qubits. You can run full algorithms on 100 qubits and actually get the right answer every time that we've ever tried it. We always get the correct solution. This is available online in our product documentation because this is available to you right now. You can achieve extraordinary performance at the scales that actually start to matter to achieve value from quantum computing. Now, if I go back to this notion of QAOA as a hybrid algorithm, what we've been able to do is build from the bottom, figure out how to optimize the hardware performance to get useful results. And then that allows us to abstract, to build on top. And so when a user of our products wants to solve this problem, instead of building the classical loop and the hardware efficient implementation and running individual circuits, you do this. You do solve QAOA. Any classical developer can write solve QAOA. It is no different than a machine learning problem executed on GPUs or CPUs. Starting from the bottom and moving up allows us to efficiently abstract in ways that has not been possible when you start top down. When you start totally abstract and you don't worry about what's going on in the real hardware, it effectively never works. So if we go back to this notion that I showed you before, we believe that it is essential to follow a path that's quite similar to what VMware laid out. Originally, you would write an algorithm specifically tailored to a specific piece of hardware. This processor, this memory, this interface. That's the hardware-defined data center. And what VMware brought to the market was the concept of virtualization, that you could separate the problem you want to solve, the algorithm that you want to run, from the underlying hardware. And when you did that, you could shift to the left in this, to the right, excuse me, for you, and you could see that we get to the software-defined data center, where now you write an abstract algorithm and you run it on any hardware. It's portable. It's disconnected from the underlying computational device, and they achieve that by virtualization. Well, now for the first time, because you don't have to worry about the physics details of what's going on inside any particular machine in order to get a useful outcome, we showed you just a minute ago that we can begin to virtualize. We can go from individual circuits and building the classical loops in QAOA to solve QAOA. You don't even need to know what hardware it's being executed on. And that allows us to begin to realize this vision of true heterogeneous computing, combining any CPU with any GPU and any quantum processor, any QPU, for any problem that matters to you without you having to write code for a specific machine. That is what we believe will actually make this technology useful to end users in enterprise. And so because the company is based in Sydney, I had to put in a Sydney Harbour Bridge joke here, that we're trying to help bridge this gap between the skill set that classical developers have, whether they're in AI and machine learning or in finance or the like, and that strategic advantage that everybody wants. Because again, as Jean-Francois and his colleagues said at BCG, 90% of value capture will go to early adopters. Our role is to make that possible for teams who have not built all of their internal human resources based on PhDs in quantum physics. This is what an analyst named Heather West at IDC called frictionless quantum software. And she said, by developing frictionless quantum software, vendors like QControl help to ease the IT developer's learning curve so enterprises can leverage current IT skills. This is our mission, to try to make this technology useful for everybody. So if you'd like to learn more about how to access this technology right now, how you can get access to our cloud service or the direct integration into IBM, I encourage you to please find us on the web. And now I can finally tell you what that is in the background. Does anybody know? Can anybody recognize it? That is a fire opal. Right? Our product is called Fire Opal. All of our products are named after opals because opals are a unique gem and they're globally coveted just like us. So that is the core product that enables you to run any algorithm on supported backends and get performance at the absolute limits of what's enabled by nature. So thank you very much for your attention. I hope you're excited to know what it's a Fire Opal, and I hope you give it a try to run real applications today. Thanks very much.